Hello, good evening. My name is Wan Muhammad Arif bin Wan Ibrahim. I'm the lead inventor for this project. With me, we have another inventors. We have Professor Dr. Muhammad Mustafa Al Bakri. We have Associate Professor Dr. Muhammad Arif Anwar, and we have Dr. Norina Hidayu in this team. So our project title Low M Hydroxyapatite, Pioneering the Future of Sustainable Ceramic Fabrication. First of all, I would like to thank the Thailand Venture Days for this opportunity for be able for us to represent our project. Okay, so we representing University Malaysia Perlis, also representing the Association of MyRIS, and also the Center of Geopolymer and Green Technology CGOTech. Okay, so let's start by give some insight or definition of what is the low M hydroxyapatite. So basically, the low M hydroxyapatite is an innovative hybrid ceramic material crafted through a groundbreaking process that significantly reduces energy consumption. Okay, so this unique method start with the activation of hydroxyapatite. So this is the recipe, basically the secret trait using the advanced alkaline activation materials AAM. So we use the methacholine for this as a precursor for this project. So this innovative approach enables desintering of hydroxyapatite ceramic at just as low as 900 degrees Celsius, where traditionally it should be sintered within temperature of 100 to 160 degrees Celsius using the conventional furnace. Okay, so this breakthrough aligns perfectly with sustainable development goals number 7, affordable and clean energy, marking a new era in ceramic manufacturing that prioritizes energy efficiency without compromising with the quality. So the novelty of low M hydroxyapatite is its activated technology, as I mentioned before, that we use methacholine for this project to activate the hydroxyapatite mixed with the alkaline activators. So a novel technique that successfully produced hydroxyapatite with a converted monoclinic structure. It is produced a monoclinic structure. So this is a remarkable achievement as it overcome the typical challenge of achieving monoclinic structure at low sintering temperature of 900 degrees Celsius, where hydroxyapatite traditionally retain a hexagonal structure. What I want to try to mention right here, basically for the hydroxyapatite, using the conventional method, we used to sinter at 1200 degrees Celsius to 1060 or 1280 degrees Celsius. Normally, we achieve the hexagonal structure. We can achieve the monoclinic structure whenever we increase the temperature up to 1400. But there is another drawback where we will lose the property decompose of the hydroxyapatite itself. Okay, so this transformation into a monoclinic structure endows low M hydroxyapatite with superior quality performance benefit in biomedical field. So I think this is one thing that everybody in the medical device or medical ceramic looking for. So before we come out with this project, we start with this problem statement. Basically, the ceramic industry, particularly in the biomedical sector, biomedical application, biomedical devices, they are facing a pressing challenge. So the high energy consumption associated with conventional sintering processor, which often operate at temperatures exceeding 1100 degrees Celsius. So this not only leads to the significant energy expenditure, but also limits the ability to produce certain material like hydroxyapatite with desired structural properties such as monoclinic structure. Okay, it's not only waste the energy whenever we increase the temperature up to 1000 or 1200 degrees Celsius, but for the case of producing the hydroxyapatite, for us to be able to get the monoclinic structure, we need to increase up to 1300 to 1400. At the same time, the drawback, have a decompose of the structure itself. And then consequently, there is a growing demand for innovative fabrication method that reduce energy usage while achieving advanced material properties. So this necessity becomes even more critical in light of global sustainability goal, specifically the goals number 7 that I mentioned just now, which emphasize the need for affordable and clean energy solution. And then the traditional hexagonal structure of hydroxyapatite basically gives some beneficial in some applications, but does not fully meet the advanced requirement of certain biomedical application, where enhanced structure and chemical stability, biocompatibility, bioactivity, osteoconductivity are important. So therefore, the development of a new approach to produce monoclinic hydroxyapatite seems to be very critical. So we have the solution. So here the product. Okay, so this slide basically to show or to compare the fabrication method of the conventional and low M hydroxyapatite. The conventional basically we sinter at 1200 above 1200 degrees Celsius, but for low M HAP, the trade secret basically we activate the hydroxyapatite prior to sinter using the same conventional furnace, but at much lower sintering temperature, which is the 900 degrees Celsius. Okay, so this is the invention. Okay, so a new technique activate HAP using alkaline activated material. The precursor, as I mentioned just now, we are using the metakaolin. So it's reduce the sintering temperature of hydroxyapatite. So selection of aluminum silicate source, optimization, concentration of activator, and determination specific drying duration. So this is what we did prior to achieve of this product. Yeah. And even for this invention, we already come with a patent filing. Okay. So this is the at our initial study that we compare the low M hydroxyapatite with the conventional hydroxyapatite. Yes, we try to sinter hydroxyapatite at 900 degrees Celsius up to 1200 degrees Celsius. So the optimum sintering temperature for the conventional method is basically above 1200. You can see or we can see that the shrinkage is a bit is is a lot. I mean, compared to what we have for the low M hydroxyapatite, we can have a great optimum sitting temperature with a good what we call it a good shrinking volume shrinkage percentage. And you can see this low end when we sinter above 1000 degrees Celsius, it start to fuse. Okay, you can see the glassy phase already found on the surface of the product. So what's the usefulness and the advantages? Low M HAP has lower sintering temperature, low impact to environment, less carbon emission due to the low energy consumption compared to conventional technique that we use higher energy consumption because we sinter at much higher the sintering temperature. And then also the low cost of production. I think this is our partner from the industry really like it. So really love and enjoy to have this and very minimum shrinkage on the optimal sintering temperature the 900 degrees Celsius for the low M HAP and 1200 for the optimum of conventional milk. Okay. So next, basically, so this is our novelty. Okay, we play around with the what we call it is solid ratio of the hydroxyapatite plus what we call it metakaolin. So we found that at the 900 degrees Celsius, we able to have the HAP with the monoclinic structure. So how we prove it? We deeply study on the X-ray diffraction technique. We found that at the 68.3 there is a peak to confirm it is a monoclinic structure. So it's confirmed for 900 degrees Celsius. We have the monoclinic, a single monoclinic phase structure for the hydroxyapatite. Okay. So this is basically the advantage of having the monoclinic phase. You can see that our low M have the highest of tensile strength. We start using the DTS method, diametrical tensile stress. So we have a 12.52 megapascal, which is good enough compared to HAP that control sample that we use here, sinter at 900 degrees Celsius, we only achieve 1.1 SIP. I'll say the highest one sit beside the monoclinic HAP, basically not the HAP phase. Okay, we're not able to get the hydroxyapatite phase, so it is no use. Okay, and then also we can see the transformation of the phase. We found that at this specific recipe, when we sintered from 800 to 1200 degrees Celsius, there is a significant phase transformation. Okay, especially at the 1100, 1200, it start to uh, it start to fuse. Okay, to form a glassy phase where we can find a noise speed of the SRD spectrum. Okay. So market opportunities, yes, it's very huge market opportunities, especially in medical application, in dental application, medical application involving restoration, filling, implant, scaffold, load bearing application, and so on. Okay, this one we can't deny it because we use the hydroxyapatite. So where the hydroxyapatite is basically the same, almost the same property with the bone that we have. Okay, and this is to show you the pattern and the publication. So we have a patent filing, basically to show that we able to file process or the secret how to reduce the sintering temperature by using these alkaline activated methods. And then so I also produce the Q2 ISI journal basically on this project, alkaline activation technique to produce low temperature sintering activated HAP ceramic. So this is basically for the academy and also for this industry who like to have this as their commercial product. And also this project basically we started for the last 4 years. I've been in the SLRI in Bangkok. So this time I'm conducting the tomography, basically tomography. So this is the collaboration and research partner with the Psychotron Thailand Central Lab and the MTech. Okay. So I think that's all is my presentation for the product UM hydroxyapatite. So thank you so much.